Right, this is a continuation of 1.2, and we're doing combining uncertainties. In the last lesson, we looked at the uncertainties in measurements, so instrumental uncertainties. We looked at the uncertainty in the measurements using a ruler, for example, which actually has two uncertainties because a ruler measures from two sides, position A, position B, and then the length is just the difference between those two positions along a ruler. Now, oftentimes, when you've measured things, you would use them in some form of an equation or form some sort of a relationship, whether that be fitting a line on a graph. So uncertainties from multiple different things start to get combined to form new things. So today's lesson is all about how do we combine those uncertainties for something else that we measure. So let's start with example. We take two measurements. These are any arbitrary measurements. I'm not going to say what they are, what we've measured it with. And the measurements that we're taking are x and y. So the value for x is x plus or minus the uncertainty in x. And then we have y plus or minus the uncertainty in y. Then we talk about a third thing that we're going to find called z. And z is what we find by putting x and y into some function. So z is the thing we will calculate using x and y. So we start first with addition or subtraction. So this is if z is calculated by the addition or subtraction of x and y. In other words, if z is equal to x plus or minus y. So if z is equal to either of those two equations, how do we then find the uncertainty in z? In the case of addition and subtraction, it's quite simple. We simply add their absolute uncertainties. So the uncertainty in z is found by adding the absolute uncertainty or uncertainties of x and y. So that basically just means that the uncertainty in z is equal to the uncertainty in x plus the uncertainty in y. Now, it might not be intuitive in some cases. So for example, if we said that z was equal to x plus y, then it makes sense because you add their uncertainties. If the number gets bigger, the uncertainty gets bigger. What might be slightly less intuitive is if we did x minus y, and then we still add their uncertainties, and you might think, well, the number gets smaller, but why does the uncertainty get bigger? Well, that's because when you think of these values x and y, it's x with an upper bound and x with a lower bound. Y with an upper bound and y with a lower bound. So when you combine those bounds together, the bounds actually get bigger even if the average value is decreased. Now, whenever you manipulate equations and you combine things, uncertainties tend to get bigger. They don't get smaller. The only times they can get smaller is if you've measured something multiple times, and then as a result of a division of a non-measurement, for example, if I measured the time of repeating things, so like a pendulum swinging, if I measured it over 10 oscillations instead of 1, and then to find the time for one oscillation, I divide it by 10. I also divide its uncertainty by 10 as well. Yeah? Because we've only got one uncertainty over the whole 10 measurements. And so if we divide it, we're actually dividing uncertainty, but that's a different case. Now, what about then for multiplication or division? So in this case, if z equals to x times y, or z equals to x over y, then the uncertainty in z is found by adding the percentage or relative uncertainties so that basically means that the error in z over z is equal to the error in x over x plus the error in y over y. Yeah.
Even in division, they add up, right?
Sorry?
Even in division, they add up.
Yeah, so it's the same even in division. You add their percentage or their relative uncertainties. Now what I've written here is their relative uncertainty, which will give you a decimal, but it's quite easy for you to figure out how to do that with percentages. Just multiply each of them by 100. That will convert them into percentages. Now if we raise to the power, so let's do raising to the power. Now this is raising a value to an integer power so we can say that z equals to x to the power of n. And if we say that n was, for example, squared, it's just going to be x times x. And if it's just x times x, we can follow what was above for multiplication. And so we would have the sigma z over z is equal to the sigma x over x plus the sigma x over x again. Well, that's just 2 sigma x over x. Without an n number of that happening, it becomes n times sigma x over x. So we've got sigma z over z equals to an n number of sigma x over x. And then finally, we've got the uncertainty for repeated measurements. So repeated measurements, for example, if I had a ball rolling down a ramp and I wanted to time how long it takes to roll down the ramp, I time it once, I reset the equipment, I time it a second time, I reset the equipment, I time it a third time, I reset the equipment, I time it a fourth time, and I do that 10 or 20 times, and then take an average. Or, I have a very long piece of wire, maybe 4 or 5 meters long, that stretches across the room, and I want to find the average diameter of that wire. So along the length of that wire, we use a micrometer and measure the diameter of the wire at different positions. We get slightly varying results, only because this is real life and slight variations happen. We maybe take 5, 6, 7, 8, 9, 10 measurements across the length of the ruler, and then we take an average of that. So when we do that, the uncertainties now change for repeated measurements, and it's no longer given by the uncertainty of the instrument, it's given by statistical uncertainty on the set of data that you have. So now we're looking at the spread of your data. So let's do repeated measurements and averages. So for repeated measurements, the uncertainty is given by the spread of the data rather than the instrument. So for example, e.g., X was measured multiple times. Each measurement is X subscript I, which for example will mean X1, X2, X3, so on and so forth. And X bar is the mean of those measurements. So to find X bar, we first need to add up all of those values. So we say that X bar is equal to the sum of Xi, and we start from, if we labeled it starting from 1, 2, 3, 4, we start from I equals to 1, and we end up at an n number of measurements. So I equals to 1, and we finish at n. So all this symbol means is, that sigma means, start summing up x values where you start when I equals to 1, so start with x1, and you add it up, x1, x2, x3, x4, up until you reach xn, which is the last value that you've measured. And if we've taken an n number of measurements, whether that be 5 or 10 or 20 or 100, to then find the mean, we add them all up and divide by the number of numbers that we have. So we divide it by n. So x bar is equal to 1 over n times by the sum of those values. Now, the uncertainty in that average is then given by the spread of that data, which is given by the range. So the uncertainty in x then is equal to plus or minus the maximum value of x minus the minimum value of x all over 2. Yep, it's the range divided by 2. Yes.
Can it be like, you know how it's plus minus 0.03?
Yeah.
For example, let's take, can it be like plus 0.03 but minus 0.01? Can that ever be a case?
No. All right, next let's talk about graphing. When graphing, you need to think about the data that you have in front of you and choose suitable scales to use. So one piece of advice that's good to follow, especially when you're doing hand-drawn graphs, is to choose scales that only go up in 1s, 2s, or 5s. Do not use 3s and 4s. Do not use 6s and 7s. So what do I mean by that? Let's draw a few graphs. So use scales which go up in 1s, 2s, or 5s. So, e.g., I'll do a few different ones. So if we do 1, 2, 3, 4, and 2, 4, 6, 8, the x-axis here goes up in 1s. The y-axis here goes up in 2s. If I do another graph, and I do 20, 40, 60, 80, and I do 500, 1,000, 1,500, 2,000. The x-axis in this case is going up in 2s, and the y-axis in this case is going up in 5s. So when I say 1s, 2s, and 5s, I'm not talking about it being 1, 2, and 5 only, but also multiples of 10 of those. So 10s, 20, 30, 40, 50, 60, that counts as going up in 1s. It's about the first digit. Yeah? And all other digits following should be zeros. 20, 40, 60, 80, again, the first digit is going up in 2s. It doesn't matter if it's 20, if it's 200, if it's 2,000, it's still called 2s. Now, why is that an important thing? Because on graph paper, the divisions are done in such a way that the subdivisions are easy to figure out what they are by using these numbers. If you go up in 3s, then you get strange numbers in between, which make it harder and longer for you to plot graphs manually. Hence why this is a good technique to use when you're plotting graphs by hand. Now, error bars are represented as bars on your graph. And they are a good visual representation of how big errors are on each of your measurements. Now, having said that, before I draw the error bars for you, I'll make note. If your errors are so small such that the error bars are not visible, then just omit them and make a comment to say that the error bars are too small to be seen. Right? Don't try to force them in even if you can't see them. If you can't see them because they're too small to be seen, omit them, write a comment. Error bars omitted because they're too small to be seen. Yeah? If they're large enough to be seen, absolutely include them, because they add value to your graphs. So, for error bars, we first represent data point as a cross, not dots, not squares, not triangles, crosses. These are hand-drawn graphs. Exam board wants you to do crosses. For digital graphs, it doesn't have to be crosses, but for hand-drawn graph, it must be crosses. And the reason why, because dots are not visible once an exam paper is scanned. Dots are not very visible once you do a line of best fit. Crosses are very visible. So you represent your data point as a cross, and then your error bars as like an elongated eye almost. So for example, if we have data which looks something like this, you might have error bars which look like that. Now, something to note, the size of the error bars can change. In the case of, for example, a voltmeter or an ammeter, in the beginning, maybe you are measuring large voltages, so you set the maximum deflection to a high value. If you set your maximum voltage to a high value, the smallest that the voltmeter can then measure is quite a large number as well. And so that will have quite a large error bar. When you then set it to the more sensitive option on the multimeter, your voltmeter can no longer measure very large numbers, but the smallest value that it can measure has now decreased, which means that the error or the uncertainty in that measurement is also less. So if you change the settings halfway into your measurements because you've gone from, say for example, a 15 volt maximum down to less than 2 volts, you would change it so that you get better precision. Your error bars can change sizes. Sometimes they'll be fixed sizes. So it depends on your data. There is no one size fits all. Error bars can be horizontal as well, but usually it's the vertical that makes the most difference. So let's think of an example. Y. Okay, so say for example, I wanted to change the height of a ramp and see how long it takes for a ball to roll down that ramp. Yeah? I would put the height of the ramp on the x-axis and I would put the time on the y-axis. Now, because the height affected the time, you would expect to have larger error bars in the y-axis than you did in the x-axis, because it was also affected by something else. And also, the time is where your random errors will come into play. When you've set the height, you're not really going to get many random errors. Because what's going to be a random error of you measuring the height of the ramp? Parallax error. But if you measure it 3 times, 4 times, it's going to reduce your parallax error. Yeah, your random errors get reduced by repeating measurements. But then if you think about the time that it takes for the ball to roll down, what's that going to be affected by? Friction between the ramp and the ball. Now the friction might vary due to the different parts of the surface of the ball, different parts of the surface of the ramp. Each time you roll, that ball might not follow the exact same line. Sometimes it might move slightly diagonally, you might not notice. It might move a different line along that ramp, because remember the ramp is 3-dimensional. It's not simple as a straight line going down. It has a certain area of that ramp. So it could be anywhere along there. It might not move perfectly straight, it might move diagonally, etc. Ambient conditions. So for example, what's the temperature of the air at that moment? How much does that temperature affect the viscosity of that air? How does that affect the drag coefficient, which puts air resistance on that ball as it rolls down? Are the windows open or closed? Is wind entering? Is there a draft that's affecting the results? And then, am I starting and stopping my stopwatch at the same time every single time? So there are a lot more things affecting what you measure as a result of you changing something. So it's the Y error bars that are the most important. But yes, you can have X error bars as well. Yeah? Now, for example, if I did the X error bars here, they're all going to be the same size because we just used the ruler to measure the height. And they'll probably be something like this, quite small. Yeah? Now, the distance from the cross to one end is the value of your error. So going up is your plus, going down is your minus. So if we said that the error bars here were plus or minus 2, it's 2 going up and 2 going down. Okay? Now, lastly, is the uncertainty for gradient and intercept. So to do this, we need to first draw a graph. So we need to do 3 lines, 3 fitted lines on this graph. We're going to do a line of best fit. We're going to then do a line of maximum gradient and a line of minimum gradient. So fit 3 lines for your data. So these are number 1, and I'll change the color here to best fit. Then number 2, a max gradient. And number 3, a minimum gradient. Now, you wouldn't actually need all 3 of those lines when you're doing your calculations, but it's good to fit 3 of them because then it will help you which 2 to choose. So you will always need the best fit, and sometimes you'll need either the max gradient or the min gradient. So to fit the best fit, you're simply going to draw a line in a way that goes through as many of these points as possible, including the error bars. So what I'll do first is I'll try to draw a line, and then I will attempt to make it a best fit. So I would estimate my best fit to look something like this. Whoops. Okay, let's try to edit this line. Right, something like that. Now your minimum gradient line in order to, your maximum gradient, sorry, in order to draw your maximum gradient line, you approximately are going to go through the bottom error bar of your lowest data point, and you're going to approximately go through the highest error bar of your highest data point. However, there is a constraint. You have to make sure that the line at least goes through every other error bar in that data. And if it doesn't, you have to adjust your ruler until you get it such that it does. So let me try, as an example, to do one. Because I'm doing it on the board, I'm going to make some adjustments if necessary. Right, so here's my first draft of a line. Now straight away I can see for the second data point and the second to last data point, my graph is in such a way that it hasn't actually gone through the data point, so that would be unacceptable. So we'll make some adjustments. So I will drag this along like so, and I will drag this slightly like so, and now it goes through, yeah? So that's now an acceptable line for a max gradient. Your minimum gradient then is going to go through the highest point of the lowest data point, so the highest error bar of the lowest data point, and the lowest error bar of the highest data point, while also going through every other error bar that exists. So now we'll do a minimum gradient. So we'll just do an initial line and then adjust it to make it fit. So it's going through that there. We have to now adjust this line to make it go through every other. There we go. Yeah? So now it's going through every other error bar with the lowest gradient possible. And those are our 3 lines. Now with those 3 lines, we get 3 different gradients. We've got the best fit gradient, the maximum gradient, the minimum gradient. With that, we get 3 different intercepts. We've got the best intercept, then we've got the minimum intercept, which is the blue line, and then we've got the maximum intercept, which is the green line. So number 4 in this list is find gradient and intercept of all 3 lines. Now remember, y equals to mx plus c is the equation of the lines, and m for a straight line is equal to delta y over delta x. Now, the uncertainty in the gradient is just equal to the difference between the best and one of the worst, so best and maximum, or best and minimum over the best. So this is equal to m best minus m min over m best or m max minus m best over M best. And then for the intercept, it's the exact same thing, but with the intercepts instead. So sigma C over C equals to C best minus C min all over C best. Or C over C equals to C max minus C best over C best. And that ends topic 1.2.